Next speaker is Wenda Li from the University of Edinburgh. Wenda and I have a lot in common because we both got our start in formal methods and formalization using Isabelle, right? And after that, nothing is the same. So Wenda has, in his dissertation, he did a lot of work on formalizing analysis, real and complex analysis, but also verified decision procedures for real closed fields or fragments of real closed fields. But like a lot of us, he has been swept up in AI and machine learning as well, and so now he brings both expertise to bear. And today he's going to tell us about scaling laws. So Wenda.
Yes, thank you, Jeremy, for this wonderful introduction. I cannot come up with a better one myself. And so this is Wenda Li, so a new lecturer in hybrid AI from University of Edinburgh. So today I'm going to talk something probably right in the middle. So we have a lot of mathematicians here, and some like AI expert here, and I want to talk about something right in between. So and the core is about scaling. So scaling law is actually, to me, is a very surprising thing. Only happens kind of in the last couple of years since ChatGPT. Now it's kind of a thing everyone knows. But what is it? Okay, I'll just come up with a very simple motivation example. So the core idea, all comes from a very, very simple task. That is just to predict the next token or to predict the next word. Say we have a sentence with a couple of words like we love formalizing. So now we ask the model what should be the next word. Okay, the model can come up with mathematics. Okay, we think, good. And the proofs, could be good, or maybe everything. Okay, then we are so happy. Or maybe sometimes the model come up with some word like a dog. A dog. We love formalizing dog, which probably does not make sense. So in this case, we'll penalize the model if they are come up with something like not coherent. And say if they are just come up with something like proofs, and then we can keep asking the model what should be next. And then the model can say, okay, we love formalizing proofs in Lin or in Isabelle. So, and then in that case, we are essentially train a model to produce a coherent sentence. And in a way that kind of the models distribution of sentences in our language. And that is an idea so-called language model. Okay, you see, it's a very, very simple idea. And it's kind of the task because a very kind of simple task because we don't need to do labeling or like we don't need to hire someone kind of to do the labeling. It's very kind of challenging, but we can just grab all this data in the world and just by feed this task to train a model, somehow the model kind of gains some sort of knowledge of everything we know. And I guess nobody expected this before 2022 or before the era of ChatGPT, because language model has been a thing for many, many years. And it's been there, but probably it's not until OpenAI who thought, okay, we can just scale it. And the kind of scale is just although there's a lot of technology, there's a lot of implementation details behind, but the idea again is just we want more data and grab all this data from the internet, and also we just make the model larger and more parameters, and it's just like that. And in the end, just remarkable things happens, like a miracle, and all of a sudden it gains something like emergence of intelligence. So before that, kind of before ChatGPT era, and people are more thinking about specialized task. Okay, we propose one task after another, and then we build a model, and we propose some tricks to solve this task, and then we beat the benchmark again and again. But then after that, it appears that we can just have a recipe to AGI. So it's just and then the model, by scaling up, the model all of a sudden gains the good performance on almost all the tasks. They are there are capabilities or emerging capabilities that does not show before, like few short learning, like instruction following and self-correction or reflection. So in a way, like the model just understands us now. So just give an example of few short learning. The idea is that so the model is kind of trained just like this, what I previously described, next token prediction. And then we say we want to do auto formalization. We want to have the model to formalize some natural sentence, some natural statement to Lin. And then we just ask the model, okay, I want to formalize the statement from natural language into Lin. And here are a few examples. And now please formalize X4. It's like before, so actually before that, maybe ChatGPT, before we scale, the model is almost like kind of down because we need to train it in order to do something, and it cannot generalize from one task to another unless we retrain it. So they are just specialized. But our humans, I think, is much more smarter than that. Even if we come to a new field which we don't know well, and then maybe you can hand over some demonstrations, some few examples, and then we can quickly adapt. So and then this is the ability that kind of kind of emerging from by scaling up, and then we can just give the model a few examples, and then all right, all of a sudden, kind of the model can do some auto formalization, can formalize in like reasonably well, so which kind of very surprising. And then the recipe becomes the bigger, the better, like the smarter, because it's kind of the idea becomes much simpler. Although there's a distributed computing, there are a lot of engineering work behind, but the core idea does not seem that complicated. And also there are computer scientists which I admire a lot, and they are claiming, okay, it's all about scale now, and the game is over. And also probably many of the AI researchers share the same belief. Okay. Now again, so that's about scaling. So we are now here for the math, for mathematical theorem proving. So what is kind of the situation in mathematical theorem proving? So here is, together with some of my friends, we wrote a position paper to ICML to survey the status quo in almost like formal mathematical theorem proving. So the core idea is kind of static prediction. So here we start with a proof state, and then for each proof state, there are many choices. There could be choice of tactics. So by applying a tactic, which will bring us to the next proof state, and then we can apply another tactic, which will bring us to another proof state. So with each proof state, we have a choice of tactics. And so the task essentially is, okay, we are having a language model, which we believe now is very smart. It's almost like a human. And we have the model to look at the proof state, and maybe some of the context, okay, like a formal math library. So by having a model to look at this thing, and then we ask the model to just give us the next tactics that is very likely to help us to prove the theorem, and then we repeat this process again and again, and then in the end we might fail or might succeed. If we succeed, we give the model some reward, and then okay, the reward will incentivize the model kind of to be better. Okay, so that's the idea. So of most of the formal theorem proving framework. So essentially, it's just a static prediction. So, and then what about scaling now? So right now, so the scaling is, I think it's more like, it's not really like what we hope for, because with other domains like ChatGPT, it's just informal reasoning. So we can scale in both data and model size. Again, so the recipe is, okay, the more data and the larger the model, okay, the better, the smarter. But here right now, with static prediction, I think the thing is that the model here is not that obvious. So from many existing open source implementation of next prediction framework, and then we observe that, okay, by scaling up the size of the model here, it does not give us better performance. So with this recipe, with this framework, static prediction framework, so the scaling we are now is only on data. Again, so we can have a lot of like statement, some from auto formalization. So say we have natural language problems, and then we can auto formalize, we can translate them into lean, and then we train our agent, proof agent on these problems, and hopefully it can get smarter. So that's scaling on the data, and also we can mutate the data. Say we have some lean statement, and we can somehow to mutate it in some various direction, and okay, we are now having more data, that's data augmentation, and then again we can use that to make our agent smarter.
Okay. I mean, normally you would link model size and the amount of data. So once you hit a sweet spot, then you scale both together. So I find it peculiar that you're keeping model size fixed but scaling up data.
Yeah, I mean, just in this framework, I think people has tried that, but it's just I know there's a scaling law, there's empirical equations, but then just the scaling, even if we have more data, but scaling the model here usually does not work very well. It's just our observation. So with this framework.
We did just never saturated the data because they are so little.
That means you're under, what are you? You're underfit.
Yeah, we can. Yeah, I'll say more about something else which kind of relevant. So, and the other part we can scale is search budget. So that is again simple. We can sample more tactics at each node, or we can explore deeper. So, and that's a search budget. So that's a situation with tactical prediction framework, which is not ideal, but still good. And okay, but there's a very recent thing happens which makes me happy. Although I'm not involved in any of this, but then I'm really happy to see this is something that came out, which is something called large reasoning model. It's kind of a very different idea. So to describe that, I'll just say a little bit of the idea of chain of thought. So say the core idea is that instead, ask the model to give us the answer directly. So we ask the model to do things step by step, and then after they finish the thinking steps, a series of steps, and then they come up with an answer in the end. So that's a very simple idea. And just to give an example of that, so say if Sarah has 3 apples and buys 5 more, and how many apples does she have? And so with chain of thought, it will probably think like this: Sarah starts with 3 apples, and she buys 5 more apples, and because 3 plus 5 equals 8, and so in the end, okay, Sarah has 8 apples. So instead of just answering, okay, Sarah has 8 apples, the model will carry out some thinking steps. And so that brings us the idea of reasoning models. So essentially, a reasoning model is a language model that is trained to explicitly bring down complex problems into intermediate reasoning or thinking steps and providing a final answer after only completing this thinking process. Okay, so with this idea, there comes a very recent work, the Kimina prover, and I know there's some authors here, and so just feel free to interrupt me and correct me if I say anything wrong about this work. So the key thing about the Kimina prover is here, and that's make it that differentiate it from the tactic prediction framework. So rather than given each proof state and predict the next tactic, it will just thinking in the middle and have a lot of things in the end without looking at the proof state, and only gives an answer in the end. So the thinking process is something like that. It's kind of an interleave of natural languages and Lin's lipid. So each thinking step is just a fragment of natural language description, and okay, there's a Lin lipid. So in the end, the model is trained to assemble all these Lin's lipid together to have a full Lin proof, and then hand over this Lin proof to Lin, and if it passes, okay, it gets some reward. So by having this, you see it's a very different framework. And then to me, the previous tactic prediction framework is a kind of myopic. So the model is not thinking like in the big picture. It just look at what it can. So what's the state now, and then how can we progress for the next step? But then with this, it's more like the model has more choice rather than looking at the state now, and it just kind of explore freely, much more freely, and then a little bit incentives or penalties at the very end. So it's more flexible. So, and with this, the Kimina prover is capable of generating much more lovely proofs to me. Yeah, because again, I'm come from the Edinburgh world, so I like declarative proofs, and so the proof from the Kimina prover looks much more like natural language proofs, a lot of halves, and which nicely break down the problem into subproblems, and then attack on each of the subproblems, and then so as a comparison, here's a like a tactic prediction prover called a BS prover. So it's one of the framework. You see, it's mostly like a sequence of tactics, which is not very readable. And so, and also, more important with this thinking model idea, the Kimina prover has a very good performance over other open source models on the market. You see the with some sample budget. It's on the mini F2F dataset. Although it has been criticized a lot, but okay, it's just to illustrate this idea. But the most importantly is that it seems to scale now. So previously, as I said, so with the state prediction model, so there's a even if we scale the model size, it does not seem to help much with the performance. But here with the thinking model based prover, so like Kimina, so this is a model with 1.5 billion parameters, and then the one with 7 billion parameters, and the one with 72 billion parameters. The performance seems steady. There's a very steady gain in performance. Okay, so that is very good news to me. I really love to see that. So it seems that the scaling law is back. Previously with tactic prediction framework, we can only scale in data and search compute, but now with thinking model, we can search we can scale in all three categories. And so at this particular point, we are probably at the kind of maybe one of the turning point of mathematical theorem proving. So which makes me think, okay, will mathematical theorem proving be solved if we just simply scaling in the current framework, which is like in other part, like ChatGPT style scales, okay, we solve the problem. But here, it's just, to me, mathematical theorem proving is still different. It's not like many other NLP tasks, but it's kind of special. So yeah, and I hope we can discuss some of the questions today. So if the problem is not solved by scaling, so what could be the missing point? So in this talk, I will share some of my perspective on encoding mathematical object of infinite size, conjecturing, problem formulation, and proof engineering. So yeah, sorry. So for many of the problems, actually, I don't have an answer. So or I have done nothing in that direction. So it's I just share some of my perspective. Maybe I will have some wonderful insight from your audience. Okay, so first about the model. So previously I just said, okay, here is a model with scale, but then I say little about the model. So actually, so the reality is the current, most of the current large language models are based on a structure called transformer. So here is kind of the structure from the classic transformer paper. Although you don't need to know anything about it, you just know this is a model and kind of a foundation model where just the people use it for everything and hope it's a way or to help us to bring us to the AGI. But the funny thing is that so when when the transformer model was originally invented, it is only for like machine learning and machine translation task. So it's probably I don't think the authors will think the model will be such influential after several years, nor the authors will kind of get its potential in reasoning. So, but for translation task, it's kind of it's a sequence to sequence task. So here we give it a sequence like a sentence like good morning and a full stop, and then we hope the model to give us a translated sentence like in Chinese good morning. So, but only later, so after that, and then people discover, okay, it can be used for many other tasks, many other symbolic tasks like integration, which I love a lot. And I know that one of the authors is a PhD student who is one of the audience here. And also a simple conjecturing task, which I have been involved. So we are kind of use the model to do some simple conjecturing in Isabelle framework. And that's about the kind of, so it's only, so the point is that it's not designed for reasoning, but it's only after that people discover, okay, it can reason. But the problem is how, like, what is its limit? So, yeah, so maybe here is like a simple test. It's a very simple game, like called the parity game, where the input is just a string of 1 and 0, and then we ask the model to count how many is there kind of a odd number of zeros in this string. Synthetic, very simple task. And then we train the model on some training set on some like strings of length up to a certain limit, but we test it on a string with much longer length. So in that case, we are truly looking into the generalization capabilities of the models rather than just some pattern matching things. So although there's like a wonderful paper of this several years ago. Although it's like transformer model, indeed they can reason out of distribution and beyond the trained length, but still you can see the performance. So here is trained. It is trained between on strings with 10 to 20 lengths, but then it is tested on like longer lenses, and then you can see that although it's not fails, it will not fail immediately, but then it's like there's a steady decline of performance after the length, after the string is getting longer. So another problem, so that's kind of beyond length generalization. So that's about mathematics. So for mathematics, I think the thing to me between mathematics and other reasoning tasks is mathematics is often about infinity. So usually we are having, in mathematics, it's very easy for us just to use some finite representations or algorithm or something to represent things that are infinite. For example, say natural numbers. So here is in Isabel. So we can easily define natural numbers using inductive definition. So a natural number is either a zero or is a successor of another natural number. And also, and on this, so we know that natural number is infinite, but then we are just through induction, we can easily define natural number in just a bounded, just a few words, a finite set of words. And also we can define operations on natural numbers like add, again, through recursive definitions. Again, it's kind of like some representation of finite length, but then that is capable to handle operations on all natural numbers. Again, we are using finite things to handle infinite project. So the same happens to O. Yeah, and also for trees and binary trees, again, we can through structural induction, we can define trees and operation on trees. So there are some research from Tanya Ringer's group on studying the capabilities of the transformer model on recursive structures, and in the end, it somehow shows that probably the model is not there yet. So it's more like the model. It kind of reasons the infinite structures, like recursive structures, in a kind of bounded depth search way. So if the problem in logic is up to a certain bound, it can do it. But then if it need to reason it to the next level, it need to resize it. We need a larger model as well. It's not like we're having a model of like only a constant size, and then we can use that to reason infinite structure. So this makes me think, okay, probably we may need to explore other models that is better suited for the mathematical reasoning task. But again, so this is just some idea. I have no idea how can we do that. Yeah, maybe I'll have some advice from you after this. So the next problem I want to talk a little bit is about conjecture. So why do we care about conjecture in mathematical theorem proving? Again, first it's from the foundation theorem, cutting elimination theorem. So say we are doing the tactic prediction framework, where we just predict the tactic. We don't have half statement, we don't have cards. So in the end, I think that theoretically the card-free theorem can be double or super exponentially longer than the one with card, the one with conjecture. So if we don't want our proof to be super long, we still need card. And also it makes the proof, again, readable and reusable. Suppose we are having hash statement, it's much easier to restructure and then to be reused. Like on the previous day, during all DBS talk, I believe that question asked why we don't, when auto informalizing like alpha proofs, and then it's because the proof is very hard to read, and then they are trying to make it in a natural language. But then, so if we can somehow directly conjecture a lot and then to generate a proof in a very human readable style in Lin, and then I think the task would be much easier. So again, and then also a question about conjecturing in the right direction. So that's about the scaling in data. So because when I say scaling data, it's like we can through mutation, data augmentation, or somehow auto formalizing natural language statement, we can gain some initial seeds, and with mutations we can kind of the seeds is like axioms, premise, or existing lemmas that we can prove, and hopefully we'll want to prove some target set, so like some lemmas. But then with conjectures is something like this purple dot, and then we hope we can conjecturing that dot can help us to gradually towards the target set. But say if we don't have a specific conjecture, okay, we may just to explore to conjecture in a random direction, but I'm not sure if this will help solve the target problem in a kind of finite budget. But then if somehow if we can conjecture in the right direction, which may help bring us to a to the target set. So previously I talked about large reasoning model again. So in comparison to the previous generation of static prediction framework, this one based on reasoning models again have a lot of conjecture. But yeah, I hope this would be the right direction. But again, I'm not sure if the signal from the reasoning model is strong enough to form like reasonably good conjectures. So again, so this is a in progress work with Marco here and Albert and Mattia, and Mattia covers this in very details on Sunday. So here I will only mention it very briefly. So the idea of this work is that we have two trainable component, a conjecture and a prover. So and we hope this conjecturing can produce some good conjectures which we can use to train the prover, and the prover will get stronger and then to help us prove more conjectures, because if a conjecture cannot be proved, so it could be false, and then it does not make much sense. So by having such a loop, so again, so this the man in the middle, the human in the middle is something we hope for the future, but right now we only consider the conjecture and the prover. So and then again, so that comes with a good question of what makes a good conjecture. So so currently we only hope our definition of good conjecture is the one that helps us to prove more theorems. So and hence we have a signal from the prover to enhance the conjecture. But we don't know yet. There may be, again, so there are many definitions of good conjectures. Maybe for me, it's like a good conjecture is the one that can bridge different branches of mathematics. But then the problem is, suppose this is my definition of good conjecture, but how can we computationally calculate this metric? So by right now, we are just explore this, and so here is some very, very preliminary results that, okay, here is a seed and something we know, and here is a target, and then we can, with our framework, we can prove some interesting things probably right in the middle. Yeah, just stay tuned, so we are working on this. Okay, so that's about conjecturing. And then, so now the next problem to me that I think might be very hard to be solved by simply scaling is about definitions or formulations. Because so here is the problem. So here is a combinatorics problem from last year's MO. So this is the problem that AlphaPool fails to solve, and you can see it's a problem that we have a snail that plays a game on a board, and on this board there are hidden monsters at the very beginning. So the snail does not know where this monster is, but then the snail starts with on the first row, and each time it can move one cell, and then if he can move to the end, to the last row, he wins. So, and then if the snail hits a monster, it will kind of instance get back to the first row, but he can still retry, and also he remembers where the monster is. So he knows, can remember the path he took. So, and then the question is, we need to determine the minimum number of values n, for which there's kind of a strategy. We need a strategy that, and then the snail can just travel to the end, like just with this n. So the minimum number of n. So you see, this is a very natural language description of this IMO problem, and so the a theorem we want to prove could be something like this. This is what I came up with, but still we also need to, there's answer guessing things that we need to have a guess that, okay, maybe some could be, might be the minimum value. And then with this, we need to say, okay, there's a list n such that there exists an algorithm, and also the algorithm needs to be a valid algorithm, and also for all the valid board, and then we execute the algorithm on this board, and then we can have something like that. So you can see it's a kind of a little bit tricky. So, and also here is a final just formulation of this particular problem where we need to use, we first need to define what the board look like, and also all this, and what does it mean by execute algorithm, because okay, here the algorithm could be non-terminating, so we also need a partial function to deal with, and some sort of monad, and then in the end it took me over 2 hours to formalize this problem using 78 lines of EW code, and I still don't know yet whether my formalization or formulation is correct, because I didn't try to prove it. So my point is that the formulation is actually a very hard problem, especially like in this case, it involves us to invent a lot of definitions and a lot of definitions before we can state just the final theorem we want to prove. So right now, if we just scaling the model, I'm not sure if the existing framework is trained to devise definitions to solve, or even to formulate some unseen problems. So I think that is probably something we may need to look into in the future. And also another example is again with, it's more messy. So it's a regular project with Manuel Ibo, Larry, and Tony, so on formalizing analytical number theory. So here I just talk about something in this formalization process where, say, we want to formalize meromorphic functions. So, and here, so this is Apostle is the textbook we are following. So we hope we can just do our formalization in the build just by looking at the textbook. But it turns out so it could be tricky, because here is yeah, before that, I don't know anything about meromorphic function, so here is the definition given by Apostle, which is kind of very big to me. So it's only singularities in the finite plane of Apostle. So okay, it's a little bit tricky for me, but then I Googled, and so where we have a much understandable definitions of meromorphic function, which is kind of an open subset of the complex plane, and there is a function that is holomorphic on all except for a set of isolated points. So that's a, and then I also checked many other textbooks. It's more or less like this one. But then how can we formalize it? So the first version is mostly like the one is most like a standard, straightforward translation of the textbook definitions. Although back then we were not sure if we want to explicitly encode the number of as a set of isolated singularity points, so we just put it here. And then it's like you see there's we need to be on an open set, and also need to be isolated singularity, and it cannot be an essential singularities. And also back then we don't have a good definition of sparse, so we're just using this simple thing like this. Yeah, we cannot have the limit of this point somewhere in the D, so in this case it needs to be kind of a sparse. And then yeah, it's a holomorphic on D except for this point. So and then, but it turns out okay, this is not very good in the end, because we have even some simple lemmas, and then we have some horrible assumptions that, again, which is even worse if we want to compose a meromorphic function with a holomorphic one. But then later, after some revisions, we have Manuel-Abel's wonderful Lorentz series libraries, and then we have very alternative definitions, which is usually not like the one on the textbook, but makes things much more happier. Yeah, but makes things much nicer. So the point is that here, so again, I think formulation is a much harder problem, which requires to synthesize definitions. Probably it's not going to be solved by scaling existing models unless we come up with some new ideas. But then the revising, like what we did with the meromorphic function, is probably viable. Yeah, we need, but then we still need get feedbacks from the approver and then to get it to iterate. Okay, so and now the question is what we can do as humans here. So to me, I think this definition is still a very challenging problem that is beyond existing AI models. So as humans, I think we can still try to write down good definitions, which is like the one that serves as an anchor point in mathematical reasoning. At least with these definitions, it should not be something that written by AI models without validated by humans. So again, so here I really appreciate the idea of formal abstract and also this recent wonderful formal conjectures project from DeepMind, which gave us beyond proofs. So, but then I think this gave us a lot of more opportunities to have more statements. Although personally, I would love to see maybe we can just have more definitions even without statement, without conjecture. So just definition sounds a very nice idea to me. Okay, so that's about formulation and definition. Now comes to the next part. So again, it's about proof engineering. So formal, to me, especially by observing the activities on the Li-Untitled chart and also see these wonderful interactions, to me, it's like formalizing mathematics or proving mathematics is not just about proving theorems. It's much beyond, and it's a social process. And so here you can see this recent thread by Terence Task. Okay, yeah, so it's very challenging problem. I know probably Kevin said, so if you formalize something that is not merged into massive, it will get rot very quickly. So there's probably, so I think there's also probably some other thing that, okay, there's no users of massive. There's only kind of developers. If you are not a developer, if you don't participate with massive, so the thing you build is going to rot very quickly, and also right now it's kind of a very tricky problem. So if you have one that is outdated and then you want to update to the latest version, okay, there's some tricks that cost a lot of effort, but then maybe that should be something we hope our AI models can do it for us. But right now, if it's just a trend to prove more theorems, so it's probably not yet in this direction. So and that is something I want to, some work of ours I want to promote here. So there are existing benchmarks, which Albert has been said a lot during his talk earlier this week. So there's benchmarks like mini F2F and a recent one, mini context. But then they are, again, so it's about proving theorems. And it will motivate us to prove more theorems. But it's not the one that may motivates us to solve the proof engineering problems. So real-world libraries like MassDeep, it has a lot of issues with refactors, bug fix, and new features. And I know it's a very hard job for the reviewers to do the PR, to check the PRs. It's very selfish effort. And so again, so existing benchmarks, they are not the one in this direction. So motivated by this, we are doing some work in progress benchmark in the direction of proof engineering, which is led by Hua Jian, a PhD student of mine at Edinburgh. So the core idea of this is, so you see the mini F2F is just given a theorem, we let the model to prove something, and then the mini context, okay, we have some context, then we prove something. But then the APE benchmark is the one the model is asked to generate a patch, kind of a diff for some for the massive. So here the input. The input is the natural language instructions of what the model needs to do, and also plus the lean source files that needs to work on, and the output is a code patch, like a diff that can be applied on the input context lean source files. So and then for this we are constructing a benchmark that essentially we mine the massive, and then we use language model to synthesize some natural language instructions, and then we also we build a pipeline, a platform that can efficiently check the answer of the benchmarked model on each revisions, on each versions of Lean, on the corresponding versions of Lean. And so in the end, if the answer compiles, okay, we have something low, but we also there's a language model as a judge things to check, okay, whether the generated patch satisfies the natural language instructions. So and here is some, maybe I'll describe this very briefly. So we mined the 90K common commits from laptop over the last 2 years or so. Yeah, and then we start with this, and then we make it fine grained, and then because some of it can span multi files, and we make it to only one file, and then even the one with 150, we try to have a chunk. We only on the chunk that is less than 100 lines of link code. Yeah, doing some like processing. So in the end, our data set you can see is the input is like comparable to the mini context benchmark, but then we have a much longer output. Yeah, and here are some preliminary benchmarks of existing models on this particular proof engineering task. You can see the Gemini is really good, but there's still a discrepancy between syntactic and semantic. Syntactic means, okay, the model, the generated patch passes Lin, is Lin happy with it, but then semantics means it satisfies the natural language instruction. So, and also some errors. So, yeah, so some errors, some preliminary analysis, although hopefully later we'll come up with more quantitative study, some qualitative analysis of the performance of each model. So, okay, that's the main idea of my talk. So here is the summary. So first I talk about scaling. So I kind of talk about, so scaling is kind of the recipe to AGI, I believe, to many of the AI researchers. But again, I believe scaling alone, like in data, simply in data or simply in data model size and search budget, just scaling in these directions alone with the current architecture probably not solve mathematical theorem proving problems for us. So in this talk, I reviewed some of the perspective, which I think we probably need something else beyond scaling. So for example, I talked about conjecturing, and so this brings up the question: what is a good signal to a conjecture? Okay, again, for computational reasons, we can define the one as the one that we can use to prove more theorems, but then there could be alternatives. We don't know. And also, yeah, a thing I'm deeply interested in, but I don't see many research in this direction, is about the infinite project of, because to me, again, so mathematics is a thing that is the area we use finite memory or finite representation to reason about infinite. So if we really want a model to reason mathematics like us, I believe it should have the capability of reason infinite structures using finite like memories or finite number of parameters. And also problems of problem formulation and definition. So for formulation, if we want to introduce new definitions, I believe it's probably beyond capabilities of existing models, and I'm not sure if it will be solved by just scaling alone. But then for refining definitions, I believe, okay, there's a chance if we have the model to iterate with prover. So, and finally, proof engineering. Again, I believe we should motivate the model to benchmark in the right direction, which is exactly like what Albert talked about from the industry perspective. I think it is something our academia people can do, because this is what we want. We want the model can help us with proof engineering, and yeah, I hope we can have benchmark in the direction that we want the model to evolve. Okay, again, so this is yeah, just my perspective, and I look forward to learning others, and also maybe possible resolutions. Again, I don't have answers, don't have my idea for many of the problems. I hope to hear answers from yours. So finally, so many of the work I described in this talk are not mine. They're just from this wonderful AI for Math community. But then for those I'm involved, I'm incredibly grateful to my wonderful collaborators, and here are they. Yeah, no, so that's the end of my talk, and I'm happy to take any questions.
Okay, questions for Wenda? Yeah.
Thank you very much for the talk. I wonder, as you're talking about scaling, how can we, do you have any thoughts on how we can reconcile complexity theory of the problem with the very good results we are having in practice? For example, I don't see people trying to solve SAT, which is simply complete with LLMs, right? And theorem proving is even much harder, right? And easy lower bound is space. So do you have any thoughts on that?
Yeah, I think that's a very, very good question, because to me, people are like already knowing that SAT is like an empty problem, but then people are still trying to build the best SAT solver to compete in this category. So I think there's a discrepancy between like theory and the practice. And also, so I think also when we are doing the theory study of SAT, we probably does not take into account of this like learning things. We just kind of explore blindly, which of course is a very hard problem. If we just explore blindly, it could be we can get lost. But if we somehow, I believe, if for the theorists, so if we can kind of bring learning into the framework of this theoretical study, I think maybe there will be interesting result I would really love to see. Yeah, Ben.
Yeah, I'm no expert in this, but how do you square the more optimistic picture of scaling that you have here with the Apple paper from last week that was quite pessimistic about the prospects of scaling? So one of their core examples was failure to do the Tower of Hanoi. Yeah, so I'm no expert. This is some genuine question.
Okay, yeah. So I heard about the Apple paper, but I didn't read it. I didn't have the time to read it. So again, my guess is that, okay, right now, probably it's a little bit about the infinite structure things. Because right now, again, so the model is kind of, it's very large. And then it can kind of exhaust all this material, all this knowledge we have on Earth. It kind of in a way overfits the whole knowledge we have. So in this case, it's very hard to come up with good benchmarks in the normal ways because it knows everything we know. But then for mathematical reasoning, I think that could be serve as a good opportunities for the benchmarking because again, mathematics is more about infinite. So and then yeah, maybe if we are kind of pushing mathematical reasoning in the direction of benchmarking existing models, I guess the model probably can learn some truly kind of generalizable capabilities. It's not just overfitting. No, it's not just memorization. Again, so I didn't read the paper, so probably I hope I answered your question.
Can I just make a comment on the Apple paper and this thing? And actually, your thing where you had a sequence and then it sort of failed. The thing is, what Apple didn't allow it to do was write a piece of code to solve the problem. And equally, you didn't do that with that, right? But now, if you ask the problem, it would actually come up with a Python code and get that 100% right no matter what length of the sequence for infinity. And equally, it would write the code to do the Tower of Hanoi. But it's just like a human being, right? A human being can't do Tower of Hanoi to 14. You get yourself confused at some point and you write an algorithm and you do it. So somehow it does capture the infinite by being able to write algorithms, I would say. And Apple not allowing them to do that was sort of a bit weird.
Ironic.
I mean, I suppose it's about what counts as reasoning.
They say they actually gave it the algorithm and then wrote it down.
No, but that's very different. That's very different. If I give you an algorithm,
The Tower of Hanoi, and say you implement it yourself, at some point you might get confused at a certain depth. It wasn't allowed to say, this is a tool, write a computer program to do it.
But also, I think part of the claim was that
let's leave the discussion of the Apple paper. So one question, we just have like another minute or two. One question.
My question is about unsolved problems. There are lots of problems that are unsolved. For example, like Collat's hypothesis, and many people worked in that direction. So there is a huge human database of attempts. Is it possible to do something in this proof software to use all this unsuccessful to the moment things to move forward?
I think it's very likely that you can just write down this conjecture into the formal conjecture repository from DeepMind, and then maybe someday you can hear about some good news.
You had a question? Yeah.
I guess to follow up on that discussion. So you were talking about earlier, right, the sort of limitations of scaling and your idea that maybe we need more new architectures. So when you see this tool use stuff, right, like embedding tools into language models, does that sort of count as like these sort of new architectures that you want to see, or do you want a more drastic shift than that? Do you think the more drastic shift would be necessary?
I think I want something more drastic, because for tool, it's like, again, we have tools that can say like computer algebra system that can reason about infinite infinite object, but that is one coded by us, and it has its limitations. It's one that is not involving. So my vision or my hope that is actually the model itself can come up with maybe representations of infinite objects on its own through learning. It's not just by use existing tool.